No, thank you so much for inviting me. I'm always excited to talk about energy efficiency. My heart is in passive house. We introduced passive house in 2007 when hardly anybody talked about it to Scotland, and it's a much more recognized standard. But many councils are adopting it now and look forward to it. But it has a much wider implication than the fringe market of passive house themselves. It's building physics. And so I want to talk about today a bit about the background of what it means, how our buildings have changed, what implications it has for our the humans that live in the buildings, for indoor air quality and climate, how different strategies have been applied and how they work out in practice, and what we can do to improve the whole landscape in terms of energy efficiency and ventilation. So I'm going to share my screen if it's okay. There's a lot of information I want to pass on. In many cases, I will have to skim over it. By all means, if you've got any questions because of any details that you're interested in, just contact me. We're very happy to explain further. There's lots of information on our webpage as well. So originally, I wanted to start off with old historic buildings. My eyes were opened at a presentation of historic Scotland, how old Victorian, Georgian, Edwardian homes worked, how they had dedicated ventilation paths, overflow vents, the sash windows, leaky floorboards, foul air chamber at the top. They had the passive stock effect through the chimney flues, and they had also moisture-absorbing materials, lime render, which absorbed humidity and released it again. So these houses worked in a particular way very well with ventilation, because obviously they needed to have the fires going, but it also in terms of humidity control. Now, modern buildings are very, very different. They are much more airtight, 3 to 5 times more airtight, no passive stock, no hygroscopic materials. But everybody assumes houses still work as they used to work. It all goes with automatically. Although the fabric and the working of these buildings, modern buildings, have changed dramatically, and the effect is quite obvious. So in terms of airtightness, buildings have increased a lot. Building regulations have tightened up on airtightness, and Scottish building standards propose a threefold strategy in terms of ventilation. You see here the measuring stick from 1 to 10. That's the air permeability at the pressure test in cubic meters per hour per square meter at 50 Pascal pressure difference applied. And the higher the number, the leakier, the lower the number, the more airtight a building is. And obviously, the more airtight, the more energy can be saved with a building. Energy efficiency mostly relates to insulation and airtightness. Both have equally the same effect on the energy efficiency in modern buildings. So in the upper bracket, natural ventilation, trickle vents, intermittent extractor fans. In the medium bracket, DMV with trickle vents in habitable rooms. And then in the lower bracket, MVHR system sets, heat recovery ventilation systems. These are the threefold strategy of SBSA, how to tackle ventilation. Now, what it means in practice is something completely different. Scottish government instigated a study on indoor air quality of modern buildings, of naturally ventilated modern buildings. And they measured the CO2, which is typically the measuring stick for indoor air quality. We all breathe in oxygen, we all breathe out CO2, and that means in a sealed environment, the CO2 will build up, the oxygen will deplete. Typically, you want to be below 1,000 ppm of CO2. That is, the benchmark between good and poor indoor air quality. The higher the CO2 level, the poorer the indoor air quality, the lesser the ventilation actually. And the study found out basically that the CO2 concentrations in occupied bedrooms were at unacceptable concentrations. The occupied mean peak of 2,317 ppm and a time-weight average of 1834 ppm. Such high levels confirm that airtight dwellings with only trickle vents as the planned ventilation strategy do not meet the standards demanded the building regulations. Reducing ventilation rates to improve energy efficiency and lower carbon emissions without providing a planned and effective ventilation strategy is likely to result in a more toxic and hazardous indoor environment with concurrent and significant negative long-term and insidious impacts on public health. Now, that was quite a punch in the face of SBSA saying, your strategy actually doesn't work in reality. And there's various reasons why it doesn't work, and we'll come to that in a moment. What we should have is a regular air exchange, regular fresh air coming in, and there is a European standard 13779, mostly for commercial buildings, which prescribes 4 indoor air quality levels: high, medium, moderate, and low indoor air quality. And in the second bracket, IDA2, medium indoor air quality, we want to be, as I said before, below 1000 ppm of CO2. What it means, we need to introduce a certain amount of fresh air per person to basically replenish the air that we consume. During the day, typically, we need about 30 cubic meters per hour of fresh air. During the night, typically about 20 cubic meters per hour to keep the air fresh. So this rule, 20-30 cubic meter per hour, that should really be in the mind of everybody who deals with the specification of ventilation systems. What happens if the indoor quality drops? Lots of studies have been done, for example, in schools and in universities. You see here the strategic thinking at about 1000 ppm drops dramatically. The higher the CO2, the more people get dozy and don't concentrate anymore properly. But there's also a long-term effect. There's short-term and long-term effects like fatigue, memory loss, circulatory problems, but also low immunity to viruses and bacteria. Unfortunately, there's also irreversible effects like on the children's lung development through poor indoor air quality. And the long-term effect is really the one that is the dangerous one. It's almost like junk food. You can eat a burger, doesn't matter. But if you live on burgers for 10 years as a main diet and chips, that will probably have an impact on your health. And so indoor air quality needs to be not only looked at the short term, but also at the long-term effects it has on the humans. And because natural ventilation is so unpredictable, the flow path through the property, the wind exposure, the state of trickle vents, internal doors, all these kind of things make the ventilation rate in a naturally ventilated building completely unpredictable. Scottish building standards have picked up on that, and they have therefore proposed to have hardwired CO2 monitors in all main bedrooms to measure actually the air quality, that people can see what the state of the air quality is. Bad air quality often can't be picked up. You can't smell it, you can't sense it. Often only when you come from a fresh, well-ventilated building into a poorly ventilated building, then you notice it. But over time, you get acquainted and don't notice anymore. So SBSA have proposed different counteractive measures like opening of trickle vents, leaving internal doors open windows, in order to improve the air quality levels according to the measured data from your CO2 monitors. Unfortunately, these action points are not really being forwarded to end customers. They're not being passed on by architects, not being passed on by builders to their end customers in order to operate naturally ventilated buildings properly. The reality shows that modern buildings with trickle vents are actually too airtight to be naturally ventilated. What you really need is to open your windows regularly, keep bedroom windows in occupied bedrooms open all night in order to achieve the air quality needed. Some people do it, some people don't, and the proof is in the pudding in the study that we've seen beforehand. But also humidity control is an issue. We all breathe out water vapor, we shower, we cook, there's evaporation from wet surfaces, and that moisture in a sealed environment can build up and lead to increased house dust mite proliferation and to mold. And all these really spores that we again breathe in. Renovation of properties is a critical one, because what we do when we renovate properties, we want to eliminate drafts, we want to insulate, we want to put in new windows often, which are better sealed, and that leads to increased air tightness and less ventilation, which again means we have higher indoor air humidity levels indoors. But also when we insulate buildings, we can never insulate them as nicely and uniform as a passive house, as a new built building. There will be thermal bridges with cold surfaces, and where then condensation will occur and again lead to mold germination and increased house dust mite proliferation. So all that releases spores into our environment indoors, which then can cause asthma, allergies, and all kinds of respiratory havoc in the occupants. Dr. Sully Howison says, if you renovate a property, the likelihood of black mold infestation triples, just because of these reasons that I mentioned. So an effective ventilation strategy is really imperative when you upgrade the fabric of a building. Unfortunately, most of the energy efficiency advice providers, like Home Energy Scotland, they don't advise on the ventilation strategy, which is a bit of a bummer, because it should be one thing they should really take into consideration. Another interesting study on indoor air quality and indoor humidity levels in terms of coronavirus has shown that actually coronaviruses are very susceptible to humidity levels. At higher humidity levels, but especially at lower humidity levels, they are much longer active than at a mid-range at about 40 to 60% humidity level indoors. So it means virus particles can retain their activity, their virulence, over a period of 14 days without hardly breaking down at relative low humidities. Whereas at 50% humidity, within a day, there is about 80% or 90% of the virus is broken down. And after 2 days, there's hardly anything left. So that shows that humidity levels indoors are actually very important for our health. So we should avoid high, but also and especially low humidity levels indoors. And there's a double warmer that low humidity levels also open up our path in our bodies for virus and bacteria to come through cracks in our mucous membranes and infect us. So just to sum it up, ventilation is critical to expel pollution, VOCs from chemicals, from cleaning agents, from carpets, from furniture, radon from the ground, particulate matter from cooking, CO2 from respiration, excess water vapor, but also bring in the oxygen we need to breathe. Getting it right is critical. Too little ventilation will lead to poor indoor air quality and high humidity levels. But too much ventilation also has a problem because it leads to low humidity levels in winter. The more you ventilate, the more you dry out your air as cold air comes in and gets heated up. And that is detrimental for the occupants as well. So the next strategy of building control is Dmav systems or central MEV systems. Why they're being treated differently? MEV, CMEV in the lower bracket, Dmav in the medium bracket is a mystery to me. Both systems work in the very same way. They extract from the wet rooms and fresh air comes drawn in from the trickle vents in habitable rooms. Building standard says we need about 0.5 air exchanges and it should be all distributed evenly. And the reality is this. We have extract points in our wet rooms, kitchen, bathrooms, utilities. These are either the central MEV extract points or the Dmav fans, which are basically like glorified extractor fans that run 24 hours a day on different levels. The fresh air comes in through trickle vents in habitable rooms, and then, as the theory says, is evenly drawn in through the property to the extract points. Now, what happens in small buildings? In small buildings with 0.5 air exchanges, we end up with a ventilation rate of 43 cubic meters per hour. What it means for a master bedroom, for example, we end up with only about 17 cubic meters per hour ventilation rate. Even in theory, that is compared to the ventilation requirements that we've seen before, and 20 cubic meter per hour per person at night, only 43%, less than half of what we really need. So these quantification tools of 0.5 air exchanges, they're nice in theory with an average building, but especially for small buildings, it is not a good tool, which leads to very poor indoor air quality and should actually not be applied as such without providing a better strategy. But the problem is also the practicality of the ventilation path. That's the next problem. Not only have we too little ventilation in general with these fans, but the reality is even worse. We have the ventilation path changing. It follows the path of least resistance. So it changes with internal resistance. Trickle vents open, trickle vents closed, curtains drawn, blinds closed, or internal doors open or closed. That will make a big difference in where the actually air is being drawn in from which trickle vents. Bedroom doors closed at night could mean that your bedroom is completely shut off from the ventilation path of such a DMEV or CMEV system, and you've got hardly to any ventilation through your room, which is occupied 8 hours a day, and you need a good air quality during the night. The only system that really provides a clear, defined ventilation path are balanced ventilation systems like MVHR. What they do, they don't only extract from wet rooms, but they also supply into habitable rooms. And so the air basically moves from your supply into habitable rooms, bedrooms, living rooms, studies, moves through the hallways into your extract rooms, and basically serves 3 zones in properties. That's what it is. You have a system, like a central system, where you extract and supply fresh air, maybe in your utility room or in a loft. And then you've got a supply ductwork and you've got an extract ductwork. The supply ductwork into your habitable rooms, extract ductwork from all your wet rooms and kitchens. And the beauty is, with a balanced system, like an MVHR system, you can actually cut out almost all your ventilation losses, which are about, with modern buildings, 35% of the heating demand of a building if ventilated properly. So in winter, let's say now here we've got -5 degrees, the air gets pre-warmed to about 18 degrees ambient level, free of charge. There's no active heating element involved at, let's say, -2 in order to achieve 18 degrees. It's just passive. The only active element are the 2 fans that move the air. So it's really a good system in operation. It's a bit complicated to set up, but it can be done properly. Now, I don't want to go into it too much. We specify ventilation systems differently. We base it on a much refined tool of specification, the Passive House design guidelines, where you provide enough fresh air for the occupants, where you extract in the right way from all the wet rooms, where you provide a good air exchange rates for all the rest of the pollution inside your home. So these systems really tackle all the demands that building control says a ventilation system should do. What does it cost? In terms of the running costs, it's really low wattage. It's completely different than air conditioning. Air conditioning, we're talking about maybe 3, 4, 5 kilowatts on energy that are being eaten up by such a system to heat or cool. MVHR is more like a passive system. Here for a 3-bedroom house, typically 40 watts on energy use. That's just a light bulb. Annual cost, running costs, let's say 40, 50 pounds. That is not really a lot, but you can save a lot. If you think about 30% of your heating energy, that can be saved. As mentioned before, what's involved is good calculations, is a duct design for your supply and extract ductwork, is different components like attenuators for noise attenuation, and then you can achieve a ventilation system which actually works very well and is completely inaudible. And that's what you want. What you don't want is all these compromises that are so prevalent in our industry, like, for example, plastic ducting. PVC ducting is relatively cheap, easy to install, rectangular or round, but the disadvantages are really prohibitive for us as a company to use these systems. They're difficult to make airtight. They've got a 3 to 5 times higher resistance to the airflow, which means much more energy use, much more noise. They have questionable hygienic properties. We've, you see here a duct that we've dug out after 4 years of use. And that's not what you want to introduce into your house. That's not the air you want to basically introduce into your house. Mold infested ductwork. As well, PVC ducting can't be really properly cleaned anymore. It's not a good system. We steer clear of that altogether. What we do use is the galvanized metal ducting, different diameters, 160, 125, 100, with crosstalk attenuators, a bit more expensive, or quite a bit more expensive, but a robust, hygienic system, durable, or a semi-rigid system, which is less expensive and easier installed, especially if you want to core through JGI joists or go through posi joists. But there's also huge differences in quality in terms of different manufacturers, so please be aware of that. Now, don't need to go into that in detail. The figure here is just the resistance to the airflow of different ducting systems. And you see here, round or rectangular ducting systems have a much, much higher resistance than metal ducting or a good semi-rigid ducting system. Now, externally, what we need is, grills or combi grills for the air coming in and the exhaust are going out. Roof cowls can be done as well, but we try to avoid them if possible. Controls, there's various controls available, modern controls with up control or nice touch screens in order to adjust the ventilation. It doesn't need to be complicated. It can be automated with humidity studs, but people who want to play around and read out energy use and temperatures and humidities, they can get all that if they want to. Just to briefly touch on, there is also different MVHR systems like decentral MVHR, which are inbuilt into an external wall, which combine, are almost ductless with the external grill, the internal grill. So these are all possible for ventilation systems. In general, for installation, we see often mistakes being made. Highly efficient system installed in a cold zone without proper insulation is just not cutting the mustard. You have all the heat losses, and your highly efficient system becomes very inefficient. So we try to avoid warm ductwork, the supply and extract ductwork in cold spaces like eave spaces or cold lofts. Insulating ductwork in these spaces can be done, but it's still a big compromise. So that's where we rather keep everything within the thermal envelope. But also the installation zone can make a big difference if you have thermal bridging, if you have thermal bypasses in your installation zone. Also for plumbing pipes, hot water pipes, heating pipes, that can make a big heat loss in terms of your pipe work. So all these compromises and gray zones should be avoided. Ducts and loft installations is always a big issue. We see here a thermal graphic image that the warm ductwork here in the loft is really radiating a lot of heat, losing a lot of heat here where the insulation hasn't been properly applied. In reality, that made a difference of about 5 degrees of the system, which it lost because of these heat losses. So when you install ductwork in a cold loft, we would advocate to keep it completely underneath the loft insulation, to keep it in a warm space without these compromises. Now, there's much more to it. We advocate that domestic ventilation is basically a trade in its own. And every trade needs proper tradesmen with proper knowledge and experience. Because domestic ventilation is a new trade, a new kid around the block. Most trades have come onto that pretty, without much background knowledge. And so the performance gaps of domestic ventilation systems like central MEV or MVHR are mind-boggling. A study in 2016 has revealed that only 16% of those systems tested had been commissioned correctly. Only 56% of the installations met the design airflow rates. More than half had huge disbalances in the system, which leads to huge efficiency losses. And only 44% of the kitchen extracts met the minimum airflow rates. And the only really positive exceptions were passive house specified MVHR systems. In almost all cases, these were meeting the flow criteria, met the design criteria, and were the positive exception because they were specified, installed, and commissioned differently. They had a proper handover to the end user who understood and operated the systems properly and maintained them. So we see training like passive house training, which is not just energy standard, but a holistic concept of training and detailing makes a big difference. So that's what a performance gap looked like, a typical one. Flexi ducting, PVC ducting with sharp ends, no silencers, no proper frost protection, noisy, inefficient, and cold. And that's how a good system should look like. Proper filtration, a proper thermal bridge-free housing of a ventilation system, quiet, efficient, and durable. We have internally good room terminals that can be adjusted and locked. We have filtered extract points in kitchens, maybe a recirculating cooker hood in a kitchen. As I said, the problem is that domestic ventilation is a trade without training. Traditional trades like plumbers and electricians, who are often tasked with installing these systems, have really very little training, up to no training in how to install them properly. A question, for example, has anyone seen an electrician with an airflow anemometer for commissioning extract fans? We haven't. Has anyone seen a building control officer actually with an airflow anemometer? We haven't. So the experience that the majority of critical installation faults actually derives from within the trades, just because they haven't been trained. And that is the problem. Although in England we have a mandatory installer training, BPEC, NIC, ESC training courses. However, bare bones they are, but there is still a certain minimum threshold in terms of knowledge that's being passed on. In Scotland, there's no mandatory training for these installations necessary yet. So also the BPEC courses, we offer, for example, BPEC as a training provider. These are just the bare bones of knowledge. A 1/2 day course with a bit of test at the end that can't really fulfill the knowledge of a trade in itself. We propose to have an extended training, maybe to passive standards, in order to achieve the quality that's needed. But also commercial ductwork installers, they are not really experienced with domestic installations. So we propose also better minimum standards for best practice in how to install and how to specify systems properly. As said, ventilation and humidity control should be treated as one of the necessary domestic trades, besides heating, ventilation, heating, plumbing, and electrical installations. And we propose a proper training for all tradespeople in installing domestic ventilation systems. Some colleges, like Edinburgh College, they have already now started to kit out training rooms for domestic ventilation installations. So that's a positive step forward. We are involved in that kind of training and equipping these colleges. Also, Borders College, they have a training suite in the Hoek facility, which we want to kit out or upgrade in the near future. So we're coming to the end. Just at the end, wood burning stoves and heat distribution. Although MVHR says heat recovery ventilation. It's not a heating system. It's a heat recovery system. It's a ventilation system which cuts out the ventilation losses. It's also not a heat distribution system. It doesn't equalize temperatures between heated and unheated rooms. It can distribute a bit more heat if so specified, for example, from a wood-burning stove. But then we would like to see a wood-burning stove with an independent air supply to maintain the airtightness integrity of the building, but also to avoid spillage of combustion fumes. What we would always advocate is having a supply point close to the stove to take as much heat away and distribute it around the house with a ventilation system. Now, at the end, this is just my take on a passive house. I love passive house. We've been, promoting passive house since 2007. It's a holistic approach, not just the typical bolt-on of solar thermal or solar PV or heat pumps that make a building green, but it's durability, healthy, good training, a holistic approach in terms of design. And that's why I like it, because it's actually best practice. Many people are scared of it, but I see it as a challenge. For me, it was really eye-opening, the lessons we learned in terms of building physics and practical installations, and also to get inspired by other examples of good design and installations. One of these examples is, for example, Dorman Estate, a small rural land owner who wanted to do something for their social tenants, built 8 passive houses. And it doesn't need to be complicated. The technology was very simple. Solar thermal panels, sealed wood stoves with a back boiler, both of them fed into a thermal store, which distributed the heat with a post heater in the ventilation system and provided obviously the hot water. So these houses are really heated with the sun and the locally sourced timber, which costs them about 35–40 pounds a year to heat their homes. So, but also the indoor air quality had a tremendous knock-on effect for one of the clients, a Canadian lady, Jane, and her husband. She had tremendous allergy issues. She had constant headaches, and the migraines and the allergy issues really wrecked her life, and she had to take heavy medication. Since she moved in the house with good F7 filtration and the MVHR system to passive standards, all these symptoms completely disappeared, the headaches on top of it. When she visited other people, all these things came back. And it's just one of these other things. Ventilation is not just about energy efficiency. It's not just about payback. It's about life quality, health, and well-being. And people who have good installed MVHR systems actually value that point, that advantage, over all the energy savings that they can achieve, because it makes a difference in their day-to-day life. So thank you so much for listening. Paul Heat Recovery, that's our company. We are just recently employee-owned, about 12 staff with installation team and a service team and a couple of designers. If you've got any questions regarding domestic ventilation, please feel free to contact us. We have a lot of information on our webpage as well. And if you want to get systems specified or priced up, please let us know as well. We are service partner to Zender and can offer good discounts to all our customers, but also good advice because of our experience with a lot of systems in Scotland.